Hi, I'm Keith Johnson from Lab M08, and this is the Spring Lab report. In this lab, we looked at the motion of a spring, which was released by Dr. Greco in this video. In this video, I chose my calibration stick to be the length of the spring at rest, and then plotted it using Tracker. In Tracker, we received this data for the X and the Y positions. Using this, we can calculate the frequency of oscillation. The frequency of oscillation in the X direction is 1.71 seconds, and in the Y direction is 1.52 seconds. This is found by looking at data points at the top of two adjacent peaks. Using Python, we can create a computer model for the spring to approximate also these values. When we look at these models together, we see that the Python model is very close to the actual model found in this from the video. They do diverge somewhat near the end, but this is mostly due to the fact that our initial conditions are not exactly the same. There are some ambient forces such as air resistance and drag we do not account for in our model, and that there is ideally a time step infinitely small used in our program. However, we only used one of 1 over 120. Having found the frequency earlier using the difference in the peaks, we can calculate the period of oscillation in each direction using 2 pi over omega equals the period. The period in the x direction is 3.67 Hz, and the period in the y direction is 4.13 Hz. Despite the fact that the period is only dependent on the mass held on the system, not on the amplitude it's pulled out, the period is different in both the x and the y directions. It should seem that regardless of where it is pulled to, it should oscillate the same in both ways. However, this does not happen because the forces are not the same in both directions. In the y direction, both the force of the spring and the force of gravity act on the object. In the x direction, only the force of the spring acts on it. This causes a different motion in the x and the y direction, leading to different periods. When we look at the energy of the system, which we define as the Earth, the spring, and the object, we find there's no net change at any point during this because no work is done. The change in the spring potential energy plus the change in the gravitational energy plus the change in kinetic energy is equal to 0. This is modeled here using our Python model, which shows us the kinetic energy, the potential energy of both gravity and the spring. And then the red line, which is along 0 for the entire plot, is the work, or the sum of all three together, and stays at 0, meaning that they all cancel out. This confirms that it is consistent with the energy principle. If we change our system, and instead of making our origin at the top of the spring, if we make our origin at this rest mass, there's no real change. The gravitational potential energy is changed somewhat, however it is not significant because while the amplitude is the same, even though the graph shifted, and all changes are balanced off by the actual motion. Bye. Hi, I'm Keith Johnson from Lab M08, and this is the Spring Motion Lab. In this lab, we looked at a video of Professor Greco releasing a spring from rest. I tracked the spring's motion in Tracker using its calibration stick of the rest length of the spring, which we knew to be 0.7 meters, and then followed it. In Tracker, this data was plotted both in the x and y directions, giving this oscillation. Using this oscillation, we can calculate the frequency of oscillation by looking at the distance between adjacent peaks. The frequency of oscillation in the x direction is 1.71 seconds, and in the y direction is 1.52 seconds. With this, with the initial conditions from our tracker data, we can create a computational model that also shows this, and model our spring motion using Python. Looking at the graphs, the model is fairly accurate, being of nearly the same oscillation. It is somewhat inconsistent. This is due to the difference in forces which are not accounted for in our Python, such as air resistance and heat loss. Also, our Python model is not ideal because it can have only a set time step instead of an infinitely small one. Since we know the frequency of oscillation, we can calculate the period. With the formula 2 pi over frequency equals period. The period in the x direction is 3.67 Hz, and the period in the y direction is 4.13 Hz. In an oscillating system, generally, amplitude does not affect period, and this system is the same. Also, however, generally, only the mass affects the amplitude, the period of a system. And so one would think that the period in the x direction and the period in the y direction would be the same because the mass is the same for this system. However, it is not. This is due to the fact that the x and y directions have different forces acting upon them, and so have a different motion and a different period. The y direction has both the spring force and the gravity force acting on it. However, the x direction only has the spring force. Because the force is greater, it causes a change, having a smaller frequency period. When we think of our system as a whole, our system is the Earth, the spring, and the mass. Within this system, no work is done, and there should be no change in energy, because they're the only things acting at this time. So the change in the potential energy of the spring, plus the change in the potential energy of gravity, plus the change in kinetic energy, should all equal 0 when summed together. Our Python model shows this accurately, with our forces being the yellow, green, and blue lines, and the red line being their sum. The red line stays at 0 consistently throughout, while the others oscillate, showing that there's no net change in energy at any point during the system's interaction with each other itself. If we were to change our system, and instead of defining our origin at y equals 0, and instead define it here, moving from the top of the spring to where the mass starts from, there would be no real change in the system, because potential energy is an arbitrary value which we define based off of relative points. There would be a change in the graph with the potential energy shifting. However, its amplitude would remain the same, and therefore the changes within it would remain the same, causing there to be no net change in the changes, or no net, i.e., no net change in energy. Thanks for listening. Bye.